All right, so we're starting chapter 9, and chapter 9 we're going to talk about series, and we're going to start off with talking about a power series. Now, a series, if you remember back from previously talking about it in Algebra 1, Geometry, and Algebra 2, and even maybe in pre-cal, a series is similar to a sequence, except a series you're going to add all the terms. Where a sequence is just a list of terms, a series is taking all those terms and adding them all together. So start with a square, 1 unit by 1 unit. Then take it in half. So we're going to take half of that unit with the very first part. And then what we're going to do is we're going to take half of what we just took or colored in and do that over and over and over again. So for instance, if I took 1/2 the first time, what is 1/2 times 1/2? Well, it's going to be 1/4. And we're going to take 1/2 of 1/4 and we're going to get 1/8. And we're going to take 1/2 of 1/8 and get 1/16. And 1/2 of 1/16 and get 1/32. And 1/2 of 1/32 and get 1/64. And you can notice what's going to happen here. You're just going to get smaller and smaller and smaller with your parts, but you're never truly going to completely fill in this square. What you're going to do is you're going to get a value that's going to be closer and closer and closer and closer, infinitely closer to 1. Now, this is an example of an infinite series that converges, because we have an infinite number of terms we can write out, but yet the sum of those equals 1, or approaches 1 is actually the better way to say it, but we say that it's equal to 1. Now, many series that we're going to look at do not converge. One example is this one. 1/1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. If we continue to add those, we're going to actually keep growing and growing and growing in value, and it goes off to infinity. Now, you're probably thinking, well, wait a minute, that doesn't make sense because my numbers are getting smaller and smaller and smaller the same way they are here. Well, that is true. But what do we notice about how these are getting smaller versus how these are getting smaller? These are getting smaller by a factor of 2 each time, or 1/2, and these are just getting smaller. So we have to learn what the rules are and what to look for to determine whether a series is going to converge or whether the series is going to diverge. And this is a divergent series right here. All right, so in an infinite series, a sub 1 plus a sub 2 plus a sub 3 plus ... plus a sub n plus continuing on. Here's another way to write it, sigma notation for a series. And all this is the sigma out front going from k equals 1 to infinity. And then in here is that nth term expression we talked about when we talked about series. So this is a sub k, where k starts at 1 and goes to infinity. So you got k sub 1, k sub 2, k sub 3, and that's where, or sorry, a sub 1, 2, and 3. That's where we get all these numbers. So this is just another way of noting this. So a sub 1 and a sub 2 and all those other things are the terms of the series. Remember, they were the terms of the sequence. Now they're the terms of the series. And the only thing that's different here is that we're adding all those things up. A sub n is the nth term, just like we did with the sequence. Now, there are also these things called partial sums, where we're going to add a set number of those terms in a series. So for instance, S sub 1 would be the sum of Well, all the terms including the first term. If we had s sub 2, that would be a sub 1 plus a sub 2, and so on and so forth. S sub 3 would be a sub 1 plus a sub 2 plus a sub 3. So S of sub n is equal to the sigma notation from k equals 1 to n of a sub k. So if we had gone in, and don't just look at this and say, oh, well, it's always going to be n. No, n can be any number you want to. Let's say it's s sub 50. Then we just replace this top number with 50 here, and we're going to have a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, a sub 7, etc., 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 all the way up to a sub 50. And then we add them all up. And that's what our s sub 50 is. Now, if we don't have the n here at all, then that's the infinite sum. And that means that this would have to go to infinity. So that's the difference in the notation. So that is called the nth partial sum, where that n is a number. That n is the same number, and we're just adding that many terms. All right, now if s sub n has a limit as n goes to infinity, then the series converges. Otherwise, it's going to diverge. But you're not going to deal with very often partial sums and convergence and divergence. We're going to deal with primarily the infinite series. All right, so let's talk about some specific types of series and get into some of our testing and ability to determine whether or not it converges or diverges. And the first thing we're going to look at is a geometric series. The same way we talked about a geometric sequence before, in a geometric series, each term is found by multiplying the preceding term by the same number r. And if you remember from sequences, r is the common ratio. So we have a plus a times r plus a times r times r plus a times r times r times r. So each time we're multiplying the previous term by r one more time. Remember, there is our nth term expression for a geometric series. Now, this series is going to converge to the sum a over 1 minus r if the absolute value of r is less than 1, but it's going to diverge if the absolute value of r is greater than or equal to 1. Now, don't miss this right here. You need to definitely write that down, because that is what you're going to find for the infinite sum of a geometric series that converges. It's a divided by 1 minus r. So this is the sum. Well, let me go ahead and put infinite sum of a converging geometric series. So if they ask you to find what this thing approaches, then that's the formula you're going to use right there. So what is this series going to approach? Well, it's going to approach a over 1 minus r, as long as the absolute value of r is less than 1. So if we're multiplying by some fraction whose absolute value is less than 1, then that thing's going to converge. It's going to diverge if the absolute value of r is 1 or more. Now, that's something that you need to file away and commit to memory. You need to know that. That is a test. First, analyze, is it a geometric series? And if it is, then the second, You want to determine if it's going to converge or diverge according to this little blue box right here. That's the complete test. Once you know it's a geometric series, that's all you got to know. So what we talk about there is we talk about -1 is less than r is less than 1 is called the interval of convergence. So that means that for r values that are in between -1 and +1, the series is going to converge. And you may be asked for an interval of convergence for different types of series, so you need to know those. All right, so we have 3 over 10 plus 3 over 100 plus 3 over 1,000 plus 3 over 10,000, ... Now, is this thing going to converge? Well, what do we have here? We have, if we write this in our sigma notation, we're going from k equals 1 to infinity. And what's the nth term expression? Well, first of all, what's my first term? My first term is 3/10. And what am I multiplying by to get from here to there? You can always take this and divide the previous one, or take this and divide the previous one to find that common ratio. But hopefully you can recognize that you're multiplying by 1 over 10. And that is to the n minus 1. So there is your nth term expression for your series there. Now, does this thing converge? Well, first thing we need to know is the absolute value of r, is it less than 1? Well, the absolute value of r is equal to 1/10, which is less than r, so the series converges. And what do we know that this thing is going to converge to? Well, we can find out by finding the infinite sum. Remember, that is the first term, 3 over 10, divided by 1 minus the common ratio. So down here, I'm going to have 9/10. So you end up with 3/10 divided by 9/10. And keep change flip, I get 310 times 10 over 9. The 10s are going to cancel out. And I'm left with 3/9, which reduces to 1/3. All right, now here's a quick thing. Watch this. 3/10, 3 100ths, 0.0, whoop, nope, one too many. 3 thousandths, 0.003. You see what's happening there? Each one of these terms is just going to add the next 3 in line. So we end up with this thing is approximately 3, 3, 3 repeating, which equals that. All right, example 2, we've got 1 minus 1/2 plus 1/4 minus 1/8 plus ... So if we want to find what this thing actually is, well, we can express, we don't have to always write the series like this. I'm just writing it so you can kind of see what's going on and how you would do it. So k approaches, k is equal to 1 and it goes to infinity. And this is a geometric series again. What are we multiplying by to get from 1 to -1/2? And from -1/2 to 1/4, and from 1/4 to -1/8. Well, we know where our first term is going to be 1, and we're multiplying by -1/2 to the n minus 1 power. All right, so once again, we have to ask ourselves, what is the absolute value of r? Well, the absolute value of r is the absolute value of this thing that we're multiplying over and over and over. So it's going to be 1/2, which is less than 1. So the series converges. And then what does it converge to? Well, s is going to be 1, the first term, over 1 minus the common ratio, which is r. Now the common ratio is actually negative 1/2. So you need to put it in as that. So negative 1/2. And then we end up with 1 divided by 3/2. So we end up with 2/3. All right, so now we had talked about how to find the infinite sum of a geometric series, but there's also an equation for you to find the partial sum. Remember, that's like if we want to find the first 50 terms of the series added together. Well, this is the equation for it. It's a little more involved, and a little more to remember. It's actually more involved than finding all the terms added together, so it's kind of weird. But it's S sub n, where n is the number of terms you're adding, is equal to a times 1 minus r to the nth power, close parentheses, divided by 1 minus r. Now, if you're remembering this, the easy way to remember this is the fact that, remember, s, just s, no s sub n. If we find the infinite series, it's a over 1 minus r, or a sub 1 over 1 minus r. So all we're doing is we're multiplying by 1 minus r to the n power. So we're multiplying r that many times. Now, if the absolute value of r is less than 1, then the limit as n approaches infinity of all this thing right here, well, it's going to go to, that part's going to go to 0. So we end up with a over 1 minus r. The reason this is going to 0, just in case you're curious and you're worried about this, remember, if the absolute value of r is less than 1, we're talking about something like 1/2 to the n power. Well, remember, that's the same thing as something like 2 to the negative n. So that means the larger this thing's going to get, the more it's going to be multiplied. What's going to happen to this? The fraction's going to get smaller and smaller and smaller and tinier, and that's why that goes to 0. So that's why that ends up going to 0. So we end up with 1 minus 0, and 1 times a gives you a over 1 minus r. All right, now if the absolute value of x is less than 1, and we let r equal x, then we get 1 plus x squared plus x to the third plus dot, 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 dot. And that is going to approach the value of 1 over 1 minus x. This is something you want to write down, and remember, you're going to see this again. This is actually a polynomial approximation of this thing. And we'll talk more about that later in this chapter. But you need to remember that 1 plus x squared plus x to the third plus x to the fourth plus x to the fifth plus x to the sixth is going to equal this value right here. Going to approach the value of 1 over 1 minus x for whatever value of x is, as long as x is less than 1. And remember, the more terms we use, the better our approximation over the interval of convergence. Remember, interval of convergence here is still going to be from -1 to 1, not including those endpoints. Think about absolute value there. We talk about absolute value of x has to be less than 1, but it also has to be greater than -1. That's where that interval of convergence came from before. All right, now a power series is in this form. The sigma going from n equals 0 to infinity of c sub n times x to the n, and that equals c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x to the third plus dot 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 c sub n x to the n plus, and continues on to infinity. This is called a power series, or this is also a power series. Now this one up here is based around x equals 0. This one down here is based around x equals a. We'll find out more about what that means later. Now these coefficients, c sub 0, c sub 1, c sub 2, are all constants. They're not changing. Once you get them set, they're set. But the x value can change as long as it's in that interval of convergence. All right, now the center, A, of this second one is also a constant. It's not going to be shifted. Once you decide this is where the center of this power series is going to be based off of, it has to stay the same. Now, as I said, this first series is going to be centered at the origin if you graphed it, and this second series is going to be shifted left or right with A being the new center. And notice that with the minus here, you're going to shift very similar to, or exactly the same way we do with trig functions and your square roots and all that stuff with the inside. Left-right shifts are going to go opposite whatever this sign is. So if this is minus 2, it's going to shift 2 units to the right. If this is plus 5, you're going to shift 5 units to the left because it's minus a negative 5. So we're literally looking at what value A is with that minus in front of it. It changes it. Now, once we have a series that we know, we can find a new series by doing the same thing to the left and right-hand sides of the equation. This includes adding, dividing, multiplying, all kinds of things, including integration and differentiation. For example, if we have 1 over 1 plus x, this is a geometric series where r is equal to negative x. Remember the one we talked about before, we had 1 over 1 minus x, and we knew that that was 1 plus x squared plus x to the third plus x to the fourth plus dot 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 going on forever. Well, what happens when we plug in the negative x right here is we end up with negative x there, negative x squared, negative x to the third, negative x to the fourth. And what's going to happen with all these? Well, any of the ones that are odd powers are now going to be what? They're now going to be negative. So 1 over 1 plus x is going to be nothing more than 1 minus x plus x squared minus x to the third plus x to the fourth minus x to the fifth. And it's going to continue on with that pattern once you've got the pattern stable, set. Any of the ones that have odd powers are going to be negative because of this negative right here being raised to an odd power. Now, if we wanted to find a series for x over 1 plus x, all we have to do is multiply both sides by x. Now that means we're going to have to multiply every single term. If we multiply this side by x, we got to multiply every term over here by x, which means each one is going to increase in power by 1. So x over 1 plus x is just 1 times x, which gives me x. Negative x times x gives me negative x squared. Positive x squared times x gives me x to the third, and we get that situation right there. So as long as you do it to both sides, it's still available. And remember, this is continuing on. You got to include those dots to show that this does not end. It's an infinite thing. All right, so with this example, you may be thinking, oh, well, I've got 1 over 1 minus x, and I want to find 1 over 1 minus x quantity squared. Well, I can just square both sides. Well, there's only one problem with this. Remember, if you have a binomial, let's say x minus 2, and you want to square that thing, it is not x squared minus 4. Remember, we have to FOIL that thing out. And that's only with 2 terms. So can you imagine when you have an infinite number of terms? So you've got to find another way to do it. Well, here's the thing. If we were to take the derivative of this, what happens? We take d dx of 1 over 1 minus x, and we could do some u substitution here, but the big thing is we want to think of this as 1 minus x to the negative 1. We don't do u substitution with derivatives. I don't know what I'm talking about here. All right, and then we can just use our same old rules with the power rule and remove the 1 out front. So negative 1 times 1 minus x squared, or sorry, to the negative 2. And then we have to multiply by the derivative of the inside, which is going to be negative 1. So these negatives are going to cancel each other out. So we end up with 1 over 1 minus x squared. So if we take the derivative of this side, we can take the derivative of this side and get what it equals. All right, so with our derivative being equal to what we're actually trying to find here, that means that we can, if we take the derivative of this side, it's going to be equal to the derivative of this side. So that means that 1 over 1 minus x quantity squared is going to equal to the derivative of this, the derivative of that, the derivative of that, continuing on forever and ever and ever. So the derivative of 1, of course, is 0. The derivative of x, of course, is 1. The derivative of 2x, of course, is 2x. The derivative of x cubed is 3x squared, and then continuing on, it would be 4x to the third plus 5x to the fourth, continuing on forever and ever and ever. That infinite series would be equal to that thing right there. So that's how you can go about doing that. Now, be careful about trying to do short versions like I was talking about just a second ago. Remember, you can't just square the top and the bottom here because you've got a binomial on the bottom. That would be, looking at this, it would be 1, if we squared the bottom, well, I mean, notation-wise it's right, but as far as the actual value is concerned, we can't get that over here because it's kind of hard to FOIL an infinite series with itself. You can try it, but it's going to be the only problem that you'll ever even work on in your entire life, and you'll never finish it. So be careful about making those jumps like that. There may seem to be easy ways, but make sure you're not violating some math rules. All right, so let's say we're still given the series 1 over 1 plus x, which is equal to this here, and we want to find what the natural log of 1 plus x is. Well, using this, how do we go about getting the natural log? Well, if we wanted to find and take 1 over 1 plus x and do some operation where we would actually get the natural log of 1 plus x out of it, we would do integration. So if we integrate 1 over 1 plus x dx, we're going to get the natural log of 1 plus x. And that would actually be the absolute value. And From there, if that's what we need to do to take this side to where we want to go, then we just integrate this side right here, and of course we would have our plus c here. And we're wondering, yeah, well, what about that? Well, we'll talk about that in just a second. But anyway, when we do our natural log when we do our integration to get the natural log on this side, we can do the integration on this side term by term. So the natural log of 1 plus x plus c is going to equal antiderivative of 1 is going to be x. Antiderivative of negative x is going to be negative 1/2 x squared. Antiderivative of plus x squared will be plus 1/3 x to the third. And then antiderivative of x to the third, increase that by 1, 4, divide by that, minus 1/4 x to the fourth, and just continue going. And then, of course, you're going to have your plus c out here. So there, your plus c's go away. If you move this plus c over there, you're subtracting plus c, and they cancel out. Because those are exactly the same plus c's. So that's where your plus c goes. Now, just to show you this is another way you can go and think about getting rid of that plus c, or where the plus c cancels itself, goes that way. But you got 1 over 1 plus t instead of using x, and then you're going to integrate from 0 to x. So you're going to end up doing what? You're going to end up substituting in the x all the way through. And when you do that, then you have to evaluate this thing at x and have to evaluate this thing at 0, and you're going to have the c minus the c, and that they're going to cancel out. So the natural log of 1 plus x is x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the fourth, dot, 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 as long as x is between negative 1 and 1. Now, once again, these power series are only going to work with the x's in between these values, because otherwise they do not converge. They diverge and they go off into different values. So they don't approach this value right here. So it only works with the x values, and we're talking about every stinking x in here is between negative 1 and 1. Now, the previous examples of infinite series approximated simple functions such as 1/3 or 1 over 1 minus x. Now, this series would actually allow us to calculate a transcendental function to as much accuracy as we like using only pencil and paper. If you're not familiar with what a transcendental function is, a transcendental function is the natural log, the common log, the exponential functions, pi, things like that. So this thing right here, this is an actual pi is not a transcendental function, sorry, scratch that. E to the x is a transcendental function, not just e. E is just a number. Natural log, any base log function is a transcendental function. But we can use these series, similar to this, to actually calculate them. If you want the 1 over 1 minus x, you can calculate that by just plugging in the stinking x. You can't do that here. That's how they calculated all the natural logs. That's how they calculated all the e to the x's. Because they're using a value, they're using this polynomial right here to calculate this. Whatever x I'm going to plug in right here, as long as it's between these two values, guess what? If I plug it in here, 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 and so on, I'm going to get a polynomial that's going to give me a decimal approximation of what this thing right here is. And with 4 or 5 terms, my approximation is very, very accurate. So that's where these series actually come from. Not only that, but this thing right here, once you get that, it's easy to do, it's really easy to do calculus with, because it's just a polynomial. What we learned way back in derivatives with a polynomial. Polynomials are our best friend because they're well behaved. They work wonders. They're easy to deal with. So if we can express any function we want to as a polynomial, then that's a big bonus for us. It may just be, a very small interval that we can use it over, but even then, it's really big. It's a big thing for us to be able to do. All right, that's the last of the first section.